Hey everybody, you made it to the reversible reactions notes. And a reversible reaction is a new kind of reaction. We haven't talked about these yet. What they do is they go to products, that's normal, but then the products will break back down into reactants. It's kind of like if you are making your s'mores again, but your little sister is standing right next to you, pulling them apart, taking them apart as you make them. So you're making the product, the s'more, but then the product is being broken back down, so you have to remake it. And then she takes it back apart and you remake it. And then she takes it back apart and you remake it. In chemistry and in that s'mores example, actually, both ways happen simultaneously at the same time. It's kind of like a double displacement reaction in which no precipitate is formed. So our forward reaction, my little arrows turned into boxes when I converted it into this program. Sorry about that. There's a forward reaction, A plus B going to C plus D, but then C plus D breaks back down into A plus B. So notice our arrows are going both ways. They go, the forward reaction is A plus B, making the product C plus D. The reverse reaction is when the product C plus D breaks down into A plus B. We still have the same definitions as before. This is always the product side. This is always the reactant side. So, reactant, whoops. So we can say the reactants form products in the forward reaction, and the products break down into reactants in the reverse reaction. Reversible reactions are said to be at equilibrium. With reversible reactions, we get to have equilibrium situations. Equilibrium is a term that you've heard of before, especially in biological terms. Equilibrium, we've talked about, or you've talked about before, your body is in equilibrium. That means it's at a constant state, no matter what you do to it. For example, there's a very narrow temperature range that your body wants to stay at. If your body gets too hot, you'll sweat to cool back down. So you maintain that temperature all the time. If you get too cold, you'll shiver to warm yourself back up again so that you'll maintain that temperature all the time. Same thing if you think about the water consumption that you have. Your body has an equilibrium amount of water that you hold constant throughout the day. If you use up that water, then your body will send you signals to drink more. If you have too much water in your system, then your body will get rid of that. So in chemistry terms, in our reversible reactions, as soon as products form, they start to break back down into reactants until the rates of the forward and reverse reactions are equal. Equal means equal. Equal means the same. So until the speed of the forward reaction is equal to the speed of the reverse reaction, once that happens, it's said the system is said to be at equilibrium. The second condition of equilibrium is that the concentrations of the products and reactants are constant. Constant meaning stable. Constant meaning the same, or constant does not mean the same, actually. Constant means stable, means unchanging. You could have more of one thing than another, but the amounts are going to be stabilized or have the same amounts. This will make more sense the more we talk about it. Right now, if you're just like, what, I don't really get it, then that's okay. Write this down. We'll talk about it more in class. With our reversible reactions, we can no longer do stoichiometry because the stoichiometry that we've been doing is for reactions that go to completion. The reversible reactions never go to completion because as soon as product is formed, it breaks back down. And because of that, we can't do normal stoichiometry with it anymore. What we're going to need to do is these K expressions. K is an equilibrium constant, so constant means not changing. Great, bells. 1 second, please. Thank you. Our K expressions are going to consist of concentrations of products raised to the number of moles. This should be an exponent. Divided by the concentrations of reactants raised to the number of moles. So this also should be an exponent. These exponents are going to come from the coefficients in the balanced chemical equation. There's a couple of rules for K expressions. Only gases and aqueous substances are allowed, not solids or pure liquids, because the concentrations of solids and pure liquids do not depend on amounts, and what we want is concentrations that depend on amounts in our K expressions. Also, second fact about K expressions is that K for any reaction is based on temperature. So the only time the actual number value for K will change is if the temperature of the reaction condition changes. Writing K expressions, here we have a chemical equation. Let me rewrite it really quickly because my formatting got a little bit messed up in this program. So it's H2 gas, hydrogen gas, plus fluorine gas, F2 gas, is a reversible reaction forming two HF gas molecules. All right, so to write a K expression, we have a giant fraction. On the top of the fraction is going to be our products. Products are always on this side of the equation. So we have the concentration of HF. That's why we use the funny brackets, because the funny brackets mean concentration. Our coefficient of 2 is going to become an exponent. So it's HF squared on the top of the fraction divided by the reactants. H2, no exponent because there's no coefficient on the H2, times F2. No exponent because there's no coefficient on the F2. This equilibrium expression is going to be what the mathematical way for us to be able to calculate amounts of products or reactants. And how this is going to work is we'll need to be given three, like in this equation, we would be given 3 of the 4 variables, and we could solve for the 4th variable. A second problem type is if you're given all of the concentrations, you could calculate a K value. Right now on your paper, I'd like you to try to write the K expression for this chemical equation. That's reversible. All right, now you're back, and I'm going to write the equation for this chemical equation. We've got SO3 squared. Ooh, what's that? SO3 squared divided by SO2 squared times O2. And the value is 4.3. This is a look-upable value on a table. So, or a given in the problem type of value. The third way to get that value is if you're actually given all of the other concentrations. For today, we're just looking at writing these K expressions and not doing calculations with them. Last thing, what do these K values mean? If K ends up greater than 1, that means the top of the fraction is larger than the bottom of the fraction, and on the top of the fraction are the products. So the products are favored at equilibrium. If the K value ends up less than 1, that means the reactants are favored at equilibrium. That means that the bottom of the fraction is larger than the top of the fraction once you calculate it out. And that's it for reversible reactions.